Okay, so the first thing I want to tell you is that I probably am one of the members of the club who has the least amount of experience with astronomy, literally. The first telescope I learned how to operate was the 20-inch at Chamberlain, and it is still the telescope I use the most. Another is I've never been to college. And so there are a lot of people here in this room who probably know a lot more than I do. But this event just fascinated me, so I decided that this was going to be something that I would look into. And then a speaker slot came open on the public night schedule, so I decided to go for it. Oh, good, it does work. Okay, so astronomy goes back as far as humanity goes back. The very first people looked up at the sky. This is a map that was drawn in China around 700 AD. It's the earliest known star map, and a good representation of how people began doing astronomy. It was all visual. Now, we're going to deviate into another area for just a little bit here. These are the four fundamental forces of physics, but they're not in the right order, weak to strong or strong to weak. Anybody want to put them in order for me?
Strong, weak, electromagnetic, gravity.
Close, not quite. Very close, though. Here's the way they are. The strong nuclear force, that's the one that binds the neutrons and protons together in the core of every atom. The electromagnetic force is actually the second strongest. Then the weak nuclear force, and to be honest with you, I'm not really sure what that does. But gravity is actually the weakest force, which you could have fooled me when I fell off a step stool on Christmas Eve. I thought it was pretty darn strong. But one of my fellow night people said, well, it is pretty weak because it's so wimpy I can lift the end of this table up against it. So, you know, when you think about that, you know, if you compare that to like an electromagnet or something like that, there's no way human force can overcome that, and we can't do anything any stronger to overcome the nuclear forces either. So, you know, at least not with our arms. So that is the order. Gravity is actually the weakest one. To go back to visual observing for a minute, the visible spectrum is just this tiny slot. If you go, and you know, from the reading I've done, there's probably bigger wavelengths than this on this end, the AM radio, and there's possibly smaller ones on the gamma ray end, but we haven't detected them yet. In the course of doing some of the research for this, I found out, I wondered, you know, how did these people come up with the idea that there might be something outside of the visible spectrum? And one of the answers I got was about the scientist Herschel, and he was curious about the visible spectrum. He got a prism and he set it in a windowsill so that it made the rainbow on the floor. And he was going to take the temperatures of each color. Now, like any good scientist, he put a control off to the side, this side of the spectrum. And he thought, well, yeah, that'll be what I compare everything else to. And so he went and he took the temperatures of every line in the spectrum, but he was so surprised when he got over here, it was warmer than everything else. And that was how infrared was discovered. So a lot of the discoveries that have been made have been by accident. Now, there was somebody else, and I can't remember who this was, and he speculated, well, if there's something to the left of infrared, then there's got to be something to the right of violet. And they named it ultraviolet before they even found it. But things like that got people interested in learning how to find out these other things that we could not see. And so I'm going to talk a little bit about electromagnetism and gravity, because I'm totally unqualified to talk about the other forces. Electric current, we're very familiar with how it works. Anything that will conduct electricity, particularly the metals, are very good at passing a stream of electrons through them. And when that happens, a magnetic field is generated as well. And likewise, if you do that, the inverse of that, this is a very, very simplified diagram of a generator. So you have some force that turns the turbine in the middle, and it has coiled copper wires around it, and then you have magnets on the outside. And so the interaction between the coiled wire and the magnets generates the electricity. So when we have that happen, the electricity comes through the wire to our home, and then on the other end, when you turn on something like your hairdryer, the motor in it has magnets, and the electricity runs through and performs the opposite function and puts out fan motor and heat. So here are some early examples of things that were created when electricity was discovered, except for the last one. What is this one? Telegraph. Right, telegraph key, this one. This is actually a radio. These are the spark generators for transmission, and this is the induction coil for tuning. I did not know that until last Tuesday night when John Duran watched my presentation and told me about it. So that's an early radio transmitter. Well, I think we probably all know what this is. It's a 1940-ish something television. And then this is an object, a radio telescope, which is one of the other ways that people have learned about astronomy. It turns out that there are a lot of things out in the cosmos that generate radio signals, and we have learned an incredible amount of information from those kinds of sources. I think this is the Green Bank telescope, but I'm not exactly sure. A few years ago, several months before Maria came through, I got to visit Arecibo. And if you ever get a chance to go, it is so worth it. They have done a beautiful job there in Puerto Rico with the Arecibo radio telescope. And so if you ever go there, it's well worth your time to rent a car or take a shuttle out there. It was an amazing experience. So what do we do with all this electricity? We watch cat videos on the internet. Okay, now on to magnetism. So we're all very familiar with magnetism. We know that the spinning core, the molten core of the Earth, helps generate this magnetic field. And right now our North Pole hasn't really figured out where it's going. It seems to be moving pretty fast. They just updated the World Geomagnetic Model to accommodate for that. Apparently it's heading from Greenland to Siberia at a high rate of speed.
Well, didn't Atlanta change the number on one of the runways because of the shift?
Well, that happens from time to time anyway. I want to say about every 20 years, some of the numbers change on runways and also on the aeronautical charts. But this is mostly impacting things that are above 55 degrees in latitude. At any rate, we've all played with magnets. So here's the big difference between electromagnetism and gravity. What happens when you've got a couple of magnets and you take the top one off and you turn it over and you try to plug it in on the bottom side? Yes, it repels. So electromagnetism can be attractive or repulsive. Gravity is only attractive. I wish they had anti-gravity, especially when I was up on that step stool. But no, except for science fiction, anti-gravity doesn't exist, at least as far as we know yet. So let's see. So there were a lot of questions in the early days about gravity. What makes it happen? How does it work? In the 1930s, there were a couple of scientists who proposed the concept of an object called a graviton. They anticipated being able to find a small particle that would account for gravity, but no such particle was ever found. Going back a little further than them, oh yes, and they were looking for it as a particle. However, somebody else we'll talk about in a minute considered it as a wave. We'll get to that. So back to the earlier times. One of the things I found out when I was doing my research was that 1 year after Galileo passed away, Isaac Newton was born. And I believe this is probably a depiction of one or the other of them trying to learn something about gravity, dropping two dissimilar sized balls off of what may be the Leaning Tower of Pisa. I'm not sure. But at any rate, early experiments were conducted like that. And they came to some good conclusions, then they came to some poor conclusions. In modern times, has anybody ever seen this one online? Okay, so this is like the coolest thing ever. This takes place in a vacuum chamber. And up here you have two devices that are linked to one release button, okay? And this is a bowling ball, probably 14 pounds or so, and of course a feather. Now remember, all the air is pumped out of this chamber. So you can Google this and watch the video online, but a scientist pushed the button and they both fall. And what happens? It's exactly right. They hit the floor at exactly the same time because there's no air to keep the feather, to interfere with the feather's fall. So, and all the scientists jumped up and down just like they do at NASA when, something successfully lands on Mars or flies by Ultima Thule.
17, there was a hammer and a feather involved in that one.
Oh, that's right. They did that too, didn't they?
Right on the moon.
Yeah, I forgot about that one. Yep. Okay, so Isaac Newton depicted here. This man was a genius. Before modern computing came along, like 300 years before modern computing really came into its own, he created equations that describe all kinds of things about celestial objects. They had already collected a lot of information, a lot of data from observations, and he came up with equations to describe the mass, the velocity, the distance, and the orbital parameters of all of the commonly observed objects. And one of the amazing things about this is that even though Einstein came along later and he had some more detailed information, Newtonian calculations are still so good that they are commonly used today because they are much simpler than the ones that Einstein wrote. One of the things that was done with his work was that it was predicted, the existence of planet Neptune was predicted because the orbit of planet Uranus had a little jig in it. There was something like, this isn't a regular orbit, there's something wrong with this. And somebody came up with the premise that there was another planet out there, and they went looking for it, and sure enough, there was Neptune. Here is one, helps to use the right thing. Here's one of his equations. Basically, this says that two objects, when they're closer together, the gravitational attraction is greater, and when they're further apart, it's less. It's a lot less the further apart they get, the inverse square law of gravitation. And, this is still used every day. And the thing that blows me away is, Newton did all this without a calculator. I can't imagine. Anyway, okay, so on to another concept. And this one was put forth by Einstein in his general theory of relativity in 1915. Now, I usually give this presentation to people at the public night. They're not astronomers. And to a lot of them, this is a new concept. But space and time do not exist separately of one another. It is one thing, and it is called space-time. And that is something that Einstein proposed. He said, if you don't have any way to measure how long it takes for something to travel through a certain amount of space, then how do you know how much space you have? And likewise, how can you have time if you don't have some space to measure it in? The two are married together. So I remember the first time I read that, it took me a little while to wrap my head around that. As if that wasn't enough. Okay, Now, we have all seen light go through a glass and get bent, right? Well, it turns out there's something else that can bend light. It's space-time. It's mass in space-time. Mass bends space-time and light. And this is another one. I mean, you know, we're talking about going into like 5 dimensions here. So I was like, wow, that's really interesting to think of a 4-dimensional object and then that it can be bent and wrapped. So, but Einstein said it was true, and so they set out to prove this just 4 years after his general theory of relativity. There was a total solar eclipse in the southern hemisphere. So there were astronomers who were ready to go to observe this on the east coast of Africa and the west coast of Brazil. And they all took observations. The thing they were looking for is this star up here was known, they knew that its position was going to be behind the sun at the moment of the total solar eclipse. So you've got this star, the sun, the moon in here somewhere, and Earth, okay, all lined up. Shouldn't be able to see that star. But during the eclipse, when the moon completely covered the face of the sun, that star became visible. And it became visible on both coasts. So that was proof of Einstein's theory about mass warping space-time and bending light. Einstein also had another prediction, though, about gravitational waves. And unfortunately, that one was not proven until after his lifetime. But to go back, these are a couple of modern depictions. This is, you have a massive galaxy in the foreground, and you have another object, probably another one in the background. And what is happening is this galaxy is bending the light around itself and showing features of the one that is behind there. There are probably, I'm trying to think of how many I read, at least 50 places in the sky that we know of where gravitational lensing causes this effect. And this is another one called the Einstein Cross. There is one galaxy in the front here, and the other 4 are images of another galaxy or star cluster behind the first one. So pretty cool stuff we can do with modern telescopes. Okay, so on to detecting these gravitational waves that Einstein predicted. This is called an interferometer. And the first interferometer that I'm aware of was devised by a scientist named Michelson. And the way that they work is that you have these 2 mirrors that are exactly the same distance apart from this beam splitter in the middle. A laser light shines on the beam splitter. Some of it goes through to this mirror and back. Some of it goes through to this mirror and back. And then together they go to a screen. And if both of the arms, the one leading to this mirror and this mirror, are equal distance, then you get a nice clear pattern like this that shows that they are the same. But if one of them moves, then this pattern becomes distorted. So what they decided to do was to create a great big old laser interferometer in order to try to detect gravitational waves. So this is a picture. We have 2 in the United States, but this was the best picture. This is the Virgo Gravitational Wave Observatory in Italy. These are, they have the kind of the brain center here in the middle where the laser is generated. And then they have these 2 long arms. And these arms, at all 3 of them, there's one in Hanford, Washington, there's one in Livingston, Louisiana, and then there's Virgo in Italy. The arms are 2.5 miles long. Each arm has the capacity, it has 350,000 cubic feet inside of it. They have to evacuate that in order for the laser to go back and forth unperturbed. And it takes 40 days to take all the air out of one of those arms. and the resulting atmospheric pressure is 1/1,000,000th of an atmosphere. Can anybody name the only other object that is bigger and might have less atmospheric pressure? Large Hadron Collider. I guess I should have said the only man-made thing. At any rate, this intrigued me when I saw it because, or when I heard of it, because I thought, wait a minute, there's a problem with just building a tunnel across the ground. Anybody know what I'm thinking of? Yeah, that's exactly it. So some of you may not know, I'm a retired air traffic controller. I worked in the tower at DIA. We have a 16,000-foot runway out there. So if I'm standing at one end of the runway with my binoculars, and I'm looking at Linda at the other end of the runway, even if we can see each other perfectly, we can't see each other below about here, because the curvature of the Earth comes up and goes down in between us. So they had to do some special engineering with these arms. They actually appear to sink into the ground in the middle and then come back up at the ends. That's so they could actually be perfectly straight. And there's a closer up picture. You can see those are pretty good size circumference for the arms. Here is the brain center for the whole thing. You can see right here that this is where the two arms begin. But 2.5 miles was not long enough for the purposes of finding a gravitational wave. First of all, anybody have any idea what the height of the gravitational wave would be, or the width of it?
How do we measure it? Because we measure it with the fabric of space-time, so we're measuring space-time with space-time.
Well, they had done some calculations. It is 1/10,000th the width of a proton. Pretty tiny. You know, this is not something you and I are going to feel when it comes by. Nothing is going to feel it. You know, if you compare that to the distance between here and Proxima Centauri, the closest star, that's 4.3 light years and like 25 trillion miles. If you wanted to measure that accurately for this purposes, or compare it to this, then a gravitational wave would be the width of a human hair. So they're looking for something very, very, very tiny. So what they did was they installed, I'm going to go back, well, I don't know, will that work? Yay! They installed these things called Fabry-Perot cavities in the arms at the ends. And so what it does is the first laser shines on one of those, and then it goes back at a slightly different angle, and then it back and forth at a slightly different angle, 280 times. And that makes the effective length of the arms 700 miles. Also, they needed to ramp up their laser light generator. 200 watts was what they had to work with. And they do this thing called recycling with mirrors, and I'm not really sure how all of that works. I didn't get clear on that. But anyway, they took a 200-watt laser and amped it up to 750 kilowatts. That's 3,750 times the original power, because that's what it takes to detect something that is this small. So back to this slide, this computer bank has a very important function in that there's a lot of noise out there. You know, you think about people walking by, trucks driving by, and even in eastern Washington, the waves lapping up over by the Puget Sound can be detected by this thing. So they had to teach the computer to subtract all the noise so that the only thing it would sense would be when a gravitational wave came by. So before August of 2017, they had 4 occasions when it happened, and those were all black hole mergers. And they got data that they had predicted, so when the information came through. So they have it set up so that when something comes in on any of these gravitational wave observatories, alarms go off, and emails go out to astronomers and astrophysicists all over the world. And that happened 4 times before August of 2017. But the problem with black hole mergers is this is what you see. Yeah. So, but they had predicted,
Clearly now.
they had predicted that there would be neutron star collisions. And the really interesting thing about this is that up until 2 weeks before this neutron star collision, they had never had all 3 observatories online at once. This happened only 2 weeks after they all came online. And the reason that was really cool is so they could find it. Well, first of all, let's talk about neutron stars. I've read a lot of information on this, and some places say that the original star is like 4 to 8 sun masses, and some of them say it's like 10 to 20 sun masses. So I don't really know. It's in the range there somewhere. But anyway, they have, they usually go supernova and then they collapse. So neutron star, when it collapses in on itself, it marries up the protons and the electrons, which instead of having an atom with a little tiny center, and it feels like it's this big because there's an electron going around like that, the electrons are packed into the nucleus, and all the nuclei are put together, and it's all solid neutrons. And it's very, very, very dense. So the average neutron star is about 1.2 to 1.4 solar masses, and they're only about 12 miles across. And here's another place where different places have different information. A teaspoon of a neutron star would either weigh 10 million tons or 1 billion tons, depending on what your source is. Anyway, it's a lot. So I actually think this is a little big. I think maybe 1 pixel on the screen here would be more appropriate to show it in relation to the Earth. Anyway, yeah, incredibly dense. And a lot of them emit radio wave radiation like pulsars. Anyway, so this is an artist's depiction of the moment that the 2 neutron stars came together. They estimate that these 2 neutron stars had been orbiting each other, getting closer and closer for 11 billion years. That's like 75 or 80% of the life of the universe. And as they got closer together, they started tearing material off each other, forming this torus around the 2 of them. And when they finally came together, they estimate that they were traveling, they weren't very far apart, but they were traveling at half the speed of light. So it was quite an explosion. And less than 2 seconds after the alarms went off at the gravitational wave observatories, Fermi, the gamma ray telescope, chimed in and said, "Whoa, we got a big gamma ray up here too." Now, the thing is, all of this traveled together 130 million light years. That's how far away this was, and that's how long ago it happened. And this is a depiction of what the gamma ray burst would look like that came out of that. Let me see what the next one is. Oh, okay. So this one is really cool. The 2 gravitational wave observatories in the United States are too close together to give us a good position, but having Virgo online in Italy enabled them to narrow it down to this smaller area here. The yellow ones are the 2 United States, which is a pretty big part of the sky they said point to, but Virgo narrowed it down, and it's in Taurus. It's in NGC 4993, I believe, and that's in the southern hemisphere. So all of the astrophysicists and astronomers in the southern hemisphere got these alarms, and they started slewing their telescopes looking for this thing, because unlike black holes, this was something you could see. So you can see right there, there's nothing at the intersection there. There is your neutron star collision. And so for the next 12 days, they collected all the data they could on this thing, because at the end of 12 days, it disappeared. Here, they don't know. I'll get to that too. But these are inputs from all different kinds of telescopes. you know, gamma ray, X-ray, radio wave, visual. And so they collected all the data they could. Some of the things that they tell us about this are that, okay, so when the two neutron stars collided, it resulted in a massive explosion, and all of these neutrons were liberated. And so they flew out into the surrounding material and interacted with all the interstellar gas and dust and created all kinds of new elements. It expanded to the size of our solar system in the space of 24 hours. And it generated the energy of 200 million times our sun's output. And they detected all kinds of stuff within this. And it's really interesting. I never knew this before, but when you have a typical supernova, it only creates the elements about 1/4 of the way through the periodic table. It takes a different type of a reaction altogether to create the other 3/4. And they had always theorized that a neutron star collision, which is also called a kilonova, would do that. And they got all kinds of data that verified that from this collision. And they estimate that there was enough material spewed out to make 10,000 Earths, 200 of which could have been solid gold, and 500 of which could have been solid platinum. So now you know where our bling comes from. So yes, at the end of all this, there are a lot of answers, but there are a lot of questions. One of the papers that was written had 3,000 authors. Yeah, I feel sorry for the aide who had to compile all that material and make sense out of it, you know. And there were people who had theories that they were like, yes, this confirms my theory, this is awesome. And there were others that were going. So they're still analyzing all the data. It's probably going to take, you know, they probably have enough to work with for at least a decade before they get to the bottom of all of the things they can learn about this. And Tim, your question about what happened to it, they don't know. The last I heard, they weren't sure. It's possible that it went over the limit and became a small black hole. But it's also possible that it's now what is left is a small neutron star. So I would imagine at some point we'll know more about that. Shortly after this, they took the 2 United States observatories offline for upgrades, but they're up and running now. And there are at least 3 new gravitational wave observatories in the works. I think the one in Germany is already up and running. Is that what you talked about before, Scott?
No, I talked about Lisa, which is going to be the space.
Oh, the space one, yeah.
Space antenna.
Yeah, I looked online today. I think there's one in Germany that's up and running, and they're building one in India and another one in Japan. So there should be more to learn about gravitational waves. Oh, and one other thing. John Grobert asked me a question on Facebook that made me dig into this. I love this. I love looking for new things. I thought the wave probably went by and just went bloop, but that's not the case. They received data for about 100 seconds before the wave died away. So just like a ripple in a pond, you know, the first one comes along and then the second one, and it took about 100 seconds for all of them to go by. So I'm looking forward to learning more about this as they get all this data crunched. And that is my presentation. Thank you.